An introduction to confidence intervals. Why do we study confidence intervals? Often, we want to know information about a large population. Actually conducting analysis on a population in order to compute the population mean or proportion or any other information about a large population would be extremely costly and time consuming. Let's think about it. Every 10 years, the government spends millions of dollars in order to answer one primary question. How many people reside within your home? They want this question answered for all American households. If it takes millions of dollars just to get Americans to answer one question, how many people reside in your home? Imagine the time and the cost for conducting a full statistical analysis or survey on a large population. In order to avoid this painstaking process, we can employ statistical inference techniques in order to estimate our population parameters. Sure, these techniques will not provide an exact value for the population parameters. However, they will significantly reduce the time and the cost and produce a reasonable estimate for the actual population parameters that we want. In general, the process for estimating a population parameter is to start with an original population. Then we would gather a simple random sample of n elements from this population. We would analyze these n elements and compute an estimate or point estimate for the population parameter. We would then use the value of this point estimate in order to make inferences about the actual population parameter. Let's examine these two cases in order to further illustrate the purpose of confidence intervals. Case 1. We want to know the mean income of workers across the United States. Instead of trying to analyze the incomes of all U.S. workers, we randomly select a sample of n workers in the U.S. and compute the sample mean. For case 2, we want to know the proportion of registered voters in the U.S. that plan to vote for the incumbent president during an upcoming election. Instead of trying to contact and analyze all United States registered voters, we randomly select a sample of n registered voters and compute the proportion of our sample that intend to vote for the incumbent president and obtain a p-bar value, our sample proportion. As long as our sample was randomly selected in a manner which makes it representative of the population, we can use the analysis of our sample to estimate the mean income for the entire population. In doing this, our sample mean would be considered our point estimate. After computing our sample mean, we can state that our population mean is approximately the value of our sample mean, or we can state the population mean is approximately equal to the sample mean, give or take some small amount. For case 2, p-bar would be the proportion of our sample that intends to vote for the incumbent president. For example, suppose we analyze the sample of n registered voters and found that P bar, the sample proportion, was equal to 45%. Statistical inference techniques will allow us to make statements such as 42 to 48% of Americans intend to vote for the incumbent president. These statistical inference techniques will allow us to make these statements simply based upon our sample proportion that we obtained, 45%. This would provide a good estimate for the population parameter that we want. 42 to 48% would be considered our confidence interval. For our example, we actually started with a 45% sample proportion estimate. The statistical inference techniques will allow us to use this estimate to create an interval for the true population parameter. In essence, what we are saying is we acknowledge that if you were to sample everyone in the entire population, the true population proportion of people that would vote for the incumbent president would not be exactly 45%. But we're estimating that it would be the value of our sample proportion, 45%, plus or minus 3%. So we are saying that the true population parameter is our sample parameter plus or minus some error. Our sampling error for this problem is 3%. By using our sample parameter in order to estimate the population proportion for this example, we would significantly cut down on the resources necessary to conduct this study. To provide an estimate of 42 to 48% would give us a ballpark estimate for the population parameter that we want. The difference between the point estimate and the population parameter is called the sampling error. When using statistical inference techniques, in order to estimate our population parameters, we must acknowledge that the two values will not be exactly equal. For the case of using the sample mean to estimate a population mean, the sampling error is the difference between the sample mean and the population mean. For the case of using the sample proportion to estimate the population proportion, the sampling error is the difference between the sample proportion and the population proportion. We will use knowledge about the sampling distribution of X bar in order to estimate the sampling error for the population mean. We will also use knowledge about the sampling distribution of P bar in order to estimate the sampling error for the population proportion. Recall the central limit theorem for means. If we have a population with mean mu and standard deviation sigma, then we can define a random variable x bar as the sample mean of a randomly selected sample of size n. The central limit theorem says that provided n is large enough, x bar is normally distributed. The population mean of x bar is the original population mean. The population standard deviation of x bar is the original population standard deviation divided by the square root of n. The standard deviation of x bar is also known as the standard error of the mean. Let's also recall the central limit theorem for proportions. If we have a population proportion P, then we can define a random variable P bar as the sample proportion of a randomly selected sample of size n. The central limit theorem says that provided n is large enough, p bar is normally distributed. The population mean of p bar is the original population proportion, and the standard deviation of p bar is the square root of p times 1 minus p divided by n. Using the central limit theorem, if x bar is normally distributed, we can draw the normal curve with the highest point occurring at the population mean of x bar, and our endpoints for this normal curve would occur at the mean minus 3 times the standard deviation of x bar and the mean of x bar plus 3 times the standard deviation of x bar. If we have the positive and negative of a z-score, then these two formulas would represent the corresponding x bar values for these z-scores. Let's shade the area in the tails of these values. We're going to define alpha as the total area in the tails of these values. Since we know that the normal curve is symmetric about the mean, half of alpha must be in the upper tail and the other half of alpha must fall in the lower tail. The area between these values is 1 minus alpha. We're going to use formulas similar to these endpoints in order to compute our 1 minus alpha confidence intervals for estimating a population mean. We refer to them as 1 minus alpha confidence intervals because 1 minus alpha of the area under the curve or 1 minus alpha of all values are going to fall within these endpoints. Since p bar is also normally distributed, we will also construct 1 minus alpha confidence intervals for p bar using formulas with structures similar to these.